post-quantum theories and some other foundations topics. All right, it looks like you're working, or at least we can see your screen. We've got some kind of a black rectangle in the middle.
A black what?
Is everyone else seeing the black rectangle? Is that
Yes.
Yep.
Yeah. There's an obstruction in the middle of the screen. We can't see your slides very well.
Oh, interesting. Let me try again. Let me change screens. See if that makes it better. So how about now?
Interesting. The rectangle had appeared for a moment, but now it's gone. And there's like a little black bar at the top. But yeah, I think we can see your slides anyway. So there's something, yeah, something odd is going on with the little rectangle at the top, but I'm not sure what's causing it. Anyway, why don't you try to give your talk?
Okay, let's see. Yeah, let's see if I can. If it becomes a problem at some point, let me know, and I can try to explain what is happening in that part of the screen.
Okay, will do.
All right, so thank you so much for the invitation to give this seminar via Zoom. It's always like very exciting for me to talk to people at Chapman, because I kind of the very few places in the world that do the kind of research that I do, Chapman is one where we have one of the closest connections in terms of topics. So it's always really thrilling to be talking to you guys. So I hope that discussions can be triggered from this talk, and that we can continue this throughout the future. So what I'm going to introduce you to today is some. Can you see my cursor, by the way? You seem to be saying no. Okay, we will see. I'm pointing at things. Okay, so what I'm going to talk to you today is about steering, which, as a little disclaimer, those of you who know David Schmidt, he is very strongly pushing forward a change of notation. And he really wants us to stop talking about steering and start talking about EPR inference. So I'm not going to get into that today. It would be good to have David for a discussion on that. So I'm going to just for, to make it easier for people to follow, just keep using the word steering. But in my papers, you might start, seeing the change of notation. So for those of you who have never heard the word steering or are not really familiar with it, steering is kind of a type of experiment that you can conduct, thought experiment or real experiment, to probe nature and try to see ways in which it behaves non-classically. So for example, in an entanglement experiment, we have two parties, Alice and Bob. And what we're interested in is the state preparation of the quantum system that they share, and checking whether that has like a classical explanation or not. There is like something truly quantum happening there. For example, if there are non-classical correlations in the local state preparations, which tells you about entanglement. And then the other thing that people are quite used to studying is also the so-called non-locality, but which I try to refer to as Bell non-classicality, in where you have two parties, Alice and Bob, and they don't really care about what is the system that they share. All that they care about is about the conditional probability distributions that they obtain between the outcomes, these classical variables that denote the outcomes of measurements that they perform on their systems. So here, X, Y, A, and B are classical labels of the measurement choices and of the measurement outputs. So steering is somehow something in between. So here we have, for example, in this particular drawing that I have here, we have Alice that has, everything that she does in her lab. We think of it as a black box. So we only care about the information that is carried by a choice of measurement that she can perform on her system, and the classical output A, the classical variable A that denotes her measurement outcome. And in the case of Bob, we don't think of him as a black box anymore. And what we do, for example, is we study the properties of the, by properties, I mean the state of the quantum system that he has access to in his lab. And of course, the particular state preparation of his quantum system might be dependent on these classical variables A and X on Alice's wing. So that's kind of a very, very nutshell on how you can think of steering if you are familiar with the other two concepts. But hopefully, towards the end of the talk, we will think of it in a slightly different way. And maybe let me get my clock here so that I don't take too much time in each slide. So questions that I usually get asked. Well, why do you care about studying steering? I said, well, it is a possible physical situation. It's a possible experiment that you can come up with. So why not try to see what we can learn from it? And also, in some cases, that particular experimental situation can actually be reflecting on the actual experiments that we're doing in our capabilities, and different parties can actually have different roles. And what for? So why do we want to study steering? Well, people like me who are more into foundations see this as an opportunity to try to see other ways on which we can learn about nature to understand it. And some of the people who are more into quantum information or applied technologies can think of this as, oh, can we use this thing or kind of this setup to devise some sort of novel or more powerful quantum information processing. So can this be, for example, a resource? And some people have studied one-sided divide-independent quantum redistribution that uses steering as a resource and so on. So there are different ways, depending on what is your take or your preference, of reasons to study this. And before, there we go. I want to make two remarks before I get into the heart of the talk, which I think is, things that we need to be on the same page about. The first one is what we steer. And, in these situations where you have Alice and Bob and you say that Alice, by performing measurements on her share of the system, somehow influences the state preparation of the system held by Bob. Well, this is kind of words which can be interpreted in different ways. So one option to try to put some formalities into these vague words is the following. Well, we fix an underlying theory, and then what we do is the system that is being steered, or the state preparation, so the system which state preparation we are somehow studying, is a system whose type is fixed by the theory. So for example, if we have an underlying classical theory explaining the experiment, then what we're going to think about is as Bob having classical systems in his lab and studying the possible state preparations of that classical system. But then another option is, well, you do not fix an underlying theory. And what you fix instead is the system type in Bob's system. So, for example, you can have an underlying theory being whatever you want, like any toy theory that you can think of or that you can conceive that people in the future might define, which has as a possible system type a quantum system. And all we care about is about the possible state preparations that this quantum system in Bob's lab can have, regardless of what is the type of the global state shared by Alice and Bob. And this second option, is the one that I will endorse in this talk, and that I usually endorse in most of my work. So I'm interested in seeing what we can learn from experiments in which Bob always ends up with a quantum system in his lab. And why? Well, there are many reasons why I prefer, I'm inclined to a foundations approach to things. So my take on this is that I want to explore like the scope of possibilities. So what is it that we can potentially see in nature when we somehow have a feeling that things could be, for example, compatible with the local description, with the local quantum description of what's going on. Sorry. So that is somehow what drove me into this sort of mindset when I started working on this some years ago. And the remark number 2 is about device independence. So this is something that lots of people have in their minds and they usually talk about, especially when talking about bad experiments, you know, and cryptography and all of that, which at the end of the day is a question of trust. So what kind of things in your experiments do you trust and you want to rely on for drawing conclusions about from the data that you observe? So for example, in the case of the Bell scenario, you have the source that produces a system and shares it between Alice and Bob. And the object that we study, the resource that we're interested in, is this conditional probability distribution, this collection of P of AB given xy, where xy are the classical labels that denote the choice of measurements by Alice and Bob, and A and B are the classical labels corresponding to the measurement outcomes. So here we don't trust anything. We don't want to trust anything about, or not we, but you know, people who work on quantum information don't trust anything about these devices. They don't want to rely on what sort of measurements they're using or what sort of description they had of their quantum system or whatever system. They don't want to rely on any of that. They just rely on the statistics that they observe. So this is like the most paranoid scenario from a cryptographic point of view. So here you have the highest standards for security, for example, in quantum redistribution, but it's more experimentally demanding if you actually want to do it in the lab. And for example, when you want to perform a particular task, you usually have lower success rates because you know the conditions that you have to fulfill in order to deem the round successful are very, very demanding. But now, on the other hand, we have Alice and Bob performing a steering experiment. So here our resource, or the object of study that we have here, is this condition, this collection of the possible states preparations of Bob's quantum system. So here, this sigma denotes the possible state preparations of Bob's quantum system, which will depend on the choice of measurement and the observed outcome by Alice. And the collection of all of these things is what, you know, is the analog of this conditional probability distribution. So this thing is called assemblage. I have a reference for it later on. So here we have some trust. So we still don't trust Alice. We don't want to use any information about what her device does or what her system is. But we do trust on whatever Bob can do, and we trust that he can do tomography, that his measurements are okay, that he knows what he's doing, and that he can tell us what is the state of his quantum system. And in this case, well, you need some assumptions to prove security, for example, but you have, on the other hand, experimentally less demanding setups and better success rates. And an example of when this could become, what's the word, like relevant, or, you know, not necessarily like a very not connected to the, you know, real life situation, is the following. So you can think of like some cryptographic setup between a client of a bank and the bank. And you don't want to believe or trust or assume that the client of the bank can have a full quantum optics lab that is reliable, you know, in their house. So you don't want to trust anything that they do. It's just, you know, their classical inputs and outputs, and that's all. But if Bob, for example, is the big bank, then you might assume that they have the resources to, have a quantum optics lab in the basement of the bank and do things with more control. So this is, when people sometimes refer to as fully device-independent setups or one-way device-independent setups. So before we, I try to easily or more friendlier, try to get you into the main topic of the talk. Let me slightly introduce you to it by discussing quantum steering very briefly. In the simplest case of scenarios, which is these bipartite setups that I've been talking so far. So here, for example, in a quantum setup, we have a source that prepares quantum systems in a particular state. This is rho B, distributes it to Alice and Bob, and then Alice performs the measurement and obtains an outcome. So mathematically, the conditional state of Bob's system in each of the rounds, so for example, in a round where X and A are observed, would be given by the Born's rule. So now, what is the non-classicality that we want to signal here or capture here with this experiment? Well, if the collection of states of possible preparations of Bob's system that we observe is only compatible with Alice and Bob having shared a quantum system prepared on an entangled state. So if these sigmas of AX, this collection is only compatible with an entangled rho AB, then steering has been demonstrated. Then is when people use the jargon that this collection of conditionally prepared states is steerable. Whereas non-steerable assemblages, so things that could have easily been obtained without needing entanglement, are things that are referred to as assemblages that have a local hidden state model, which is the analog of local hidden variables or, classical ontological models and that sort of thing. So what do we mean by a local hidden state model? Well, there are different ways that people think of it and that actually have a kind of, at the end of the day, similar mathematical expression. So if we say that, well, what we wanted to do in this quantum experiment was to somehow certify whether we had entanglement, then a local hidden state model is a model provided for this collection of states, which is given or can be equivalently produced by Alice and Bob sharing an unentangled state. So in this case, a separable one. So notice that after Alice has performed her measurements, then we obtain this particular form for the types of quantum states that Bob can observe in his lab. But then another way that people think of it as well is, well, local hidden state model is one in which you have a classical quantum state preparation source. So the source sends a classical lambda to Alice, which then she uses as a response function, and then a quantum state to Bob, a quantum system there. And then what Bob observes at the end is the basically this raw lambda, but weight in a decomposition depending on this P of A given X lambda. And finally, the other equivalent way of seeing or assessing classicality in a steering experiment is by thinking of local operations and shared randomness. So if you can create these states using a LOSR protocol, then you say that your assemblage, your collection of conditionally prepared states, admits a classical description. So here you have your source that prepares a lambda, a classical variable lambda, distributes it to Alice and Bob, and then Alice, uses that and produces an outcome A, given her choice of measurement X and the variable lambda that she received, and then Bob uses the information of lambda to locally prepare the state of this quantum system. So those are three different ways of thinking about classicality. And, you know, just a pictorial description of this is that you have like the full set of assemblages that Bob can have, or that you can, you know, Alice and Bob can observe in this steering experiment. And you have the set of all of the ones that you can realize with these quantum systems. But there is like a subset of that, which is a strict subset, which are the ones that meet this classical model. So how can we tell, given an assemblage, if it's steerable? Well, there are steering inequalities that you can come up with to certify the, say, non-classicality of a given assemblage, or you can also look for an explicit local hidden state model. So this would be, these steering inequalities would be like the analog of Belen inequalities or non-local games that people sometimes talk about. So that we kind of, you know, that was like an introduction to steering and to the jargon and the way that we think about things. So now one of the main things that I want to discuss here as well is what happens when we think of things beyond quantum theory. So far I've talked about Alice and Bob sharing a quantum system. And why should we, or it's okay for us to be bothered about trying to explore or entertain the possibilities beyond quantum theory? And for that, I have this nice quote that I heard at a talk once. And this is an extract from a book by Michelson, which is a Nobel Prize winner. And he says the following. He says, the more important fundamental laws and facts of physical science have all been discovered. And these are so firmly established that the possibility of their ever being supplanted in consequence of new discoveries is exceedingly remote. So this was Michelson in 1903, saying that classical physics was the end of it, and that all that was left to do in science was to just, you know, work out the details of the consequences of it, but that it was definitely not going to be supplanted. And this was 2 years before the photoelectric effect. So he couldn't have been more wrong, in a sense. So one, you know, this makes you wonder whether you should be a little bit cautious and say, well, even though we are quite comfortable at the moment with quantum theory, and we might feel like it really explains, you know, lots of the physics that we observe, might not necessarily be the ultimate answer to how to describe nature, especially, you know, given that we still don't know how to make sense, you know, with general relativity and that sort of thing. So we might want to be a little bit cautious and keep an open mind. But even if you are like devoted that, you know, quantum theory is right and nothing is going to change, and, you know, that's the ultimate answer, well, you can use this as an exercise to try to understand the limitations that quantum systems have for different applications. So how non-classical can quantum theory be, and how this limit on its non-classicality can affect the things that we do with these quantum resources. So whichever, you know, your attitude is, I think it's observing or entertaining possibilities beyond quantum is a good exercise. So here I want to basically now walk you to the concept of steering beyond quantum theory. But in order to somehow introduce you to it, I want to first discuss very briefly the case of a Bell experiment or the Bell scenario, so that you can see then by analogy how we are trying to conceptualize this. So remember that in a Bell scenario, we have, you know, Alice and Bob and this source that prepares the system, sends it to both, and what we study are the correlations. So what is like one of the most basic things in the Bell experiment? Like something that doesn't matter if it's quantum, classical, or whatever. What is like the basic in the definition of the Bell experiment? Well, Alice and Bob are very far away, and they perform space-like separated actions on their share of the system. So that is a given, regardless of which theory you have, and that is like one of the minimum requirements that you need here. So that is captured by this collection of linear constraints, which is known as the non-signaling principle. So basically, when you take the marginal, for example, in this case, the first case, over Bob's outcome, what you obtain is a marginal distribution, a conditional probability distribution that does not depend on his choice of measurement. So in this way, Alice's marginal distribution is well defined. And similarly, if you forget about Alice. So if we think only from this point of view, like operationally, without thinking of the details of the particular theory that might be underlying our experiment, then we can just think about the following. We have the object of study, which are these correlations, and the most generally allowed object is, conditional probability distribution that satisfies the non-signaling principle. So those are like the two main conclusions that we can draw before we start adding other properties or requirements provided by the particular theory that we are assuming underpins our experiment. So once we're there, then we can totally forget about the source, and we can just study this thing and not think about what the particular mediator or system that provides these correlations is, but just study the correlations after themselves. And when you're here, then, well, you, but in this case, Popescu and can say, well, in this very abstract and detached from a particular physical theory scenario, you can now go and take pen and paper and define mathematically correlations that satisfy these constraints. So they are well-defined mathematical objects that satisfy this non-signaling principle. And one of the most famous one is the Popescu and Roerich box, which is a correlation that is actually quite intuitive to think of it, because basically, if it is for a bipartite scenario, when I have this expression here, the classical variables a, b, x, y can take values 0 or 1. So basically, what this says is that when the choice of measurements, when one or both of the choices of measurements correspond to the label 0, then the outcomes are correlated. However, when both choices of measurements correspond to the label 1, then the outcomes are anti-correlated. And that can be shown that cannot be reproduced by quantum theory. So you cannot find a source that prepares a quantum system and quantum measurements for Alice and Bob that can reproduce these correlations. So now let's try to think about this. And when you have this more general approach to correlations, then you end up with a kind of a depiction like this. So you have this green set, which is a set of correlations that you can produce with quantum systems. This gray set inside this triangle, which is the one that can be realized with classical resources. And then you have this very big one, which I draw here as the pentagon, which is a set of correlations that satisfy the non-signaling principle, and they're like the most general ones compatible with, the assumptions of a Bell scenario. So now that we have that in mind, let's see how we can approach this from how we can apply this reasoning to a steering experiment. So here, let me do it for a bipartite experiment, but also works for more experiments as well. So like I said before, we have the source, Alice and Bob. Bob performs tomography and can, see what the state of his system is. And Alice chooses measurements and obtain outcomes. So here, Similarly to the case of a Bell scenario, Alice and Bob are distinct parties that perform space-like separated actions. So from an operational point of view, they need to satisfy the non-signaling condition, but now formulated for the case of assemblages rather than correlations. So in this particular case, what it means is that Alice, which is the one that has a choice here, so she's the one that has a choice X, she shouldn't be able to communicate information to Bob by using this variable X. So what that means is that when we sum up the possible outcomes that she can obtain, then the state that we obtained for Bob's system cannot depend on the choice of variable X. So from a more like a quantum jargon, because I remember having lots of conversations with Sandu about this, what this would mean is that so if you have a choice of X, so for each choice of X, what you do is you have an ensemble of states. And this, what it means is that the different choices of X or the different ensembles correspond to the same quantum state at the end of the day. So there are different possible ensembles for the same quantum state in Bob's lab, marginally. So from this point of view then, so if we just think operationally and with this non-signaling constraint in mind, we can do something similar. So now the object that we study is this assemblage, so this ensemble of ensembles. And here's where I have the reference that I was mentioning at the beginning to Pusey's paper where he coined this terminology. And then the most generally allowed object in a steering experiment, then complying with this, the definition of the scenario is just non-signaling assemblages. So now, we have a door opened to study steering without the assumption that quantum theory is underpinning the experiment, without having to come up with a description of what the source does. And here you're like, well, let's go and do exactly what we did for the case of correlations. And you might be a little bit disappointed because there is actually a theorem that says that in this particular scenario that I've been talking to you, that I have been talking about for the past half an hour or so, all of the assemblages that satisfy the non-signaling principle admit a quantum realization. So there is nothing that we can see here beyond what quantum theory can explain. However, if you go to a multipartite scenario or a modified bipartite scenario, then loads of opportunities open. And just to give you a little glance of the kind of things that you can have in mind when looking at post-quantum steering, they are the following. So examples can be found in multipartite steering scenarios. So here we have 3 parties, and here Alice and Charlie are both black box parties. And so now the state preparation of Bob's system will depend on the labels AC, XZ. And now in this kind of scenario where we have different, non-signaling constraint among all of the parties, you can see, you can come up with examples of post-quantum steering. And in the case of a bipartite scenario, you also have what we branded as Bob with input scenario, which is now a scenario where Bob can influence the state preparation of his system by choosing a classical variable y, the value of the classical variable y. And similarly, there is another scenario, which is the instrumental steering scenario, which basically takes its name because of the instrumental causal network, causal structure, sorry. And here, basically, it has a very similar flavor to the Bob with input, but the value of Bob's variable y is set to coincide with Alice's outcome, which it might look like cheating because there seems to be some kind of communication here, but you can think of it, if it's better for you, as a kind of a post-selection of a Bob with input scenario. And things like work out in the end, and you can see how classical quantum and post-quantum assemblages arise in this scenario as well. And just to complete this big picture approach to this post-quantum steering, what you end up at the end of the day is with something similar than in the case of the space of correlations in a Bell scenario. But now instead of having 2 polytopes and 1 convex set, we have 3 convex sets. One with the assemblages that have that admit the local hidden state model. Then the one that includes it is the set of assemblages that have a quantum realization, and then the larger one is the set of assemblages that includes the quantum one, which satisfy the null signaling principle. And now there a question to the one that I was asking at the very beginning, which is, well, if we have an assemblage, how can we tell if it's post-quantum or not? I asked you before, how can we tell if it's quantum or not? And it was quite easy. Now, how can we tell if it's post-quantum? Well, that's an open question. We still don't have a definite test that tells you that. And I kind of feel like there might not be one. And a useful but not complete tool is, and actually there is like a hierarchy, like similar to the MPA hierarchy for those who are familiar with it. But for the case of steering scenarios, for all of these different scenarios that I've mentioned. But of course, each of those is like an infinite hierarchy of semi-definite programs. So it would take a long time, an infinite amount of time to answer this question if you want with those numerical tools. So I will use
Anna, are you there? I think you've frozen up on our end. I think we lost her. Let's give her a minute to return.
Hopefully she'll see what happened and log back in. I don't know how good the internet in Poland is.
Maybe meanwhile, somebody volunteer to give definition what one will call steering.
Yes, so I think the simple effect is that by measuring a local observable on one party, you can change the state of another party. So in a typical entanglement experiment, if you choose to measure X or Z on Bob's qubit, then you force the state of Alice to be in an X eigenstate or a Z eigenstate. So you can change the state of the other party by choosing to measure on your party. That's what we're talking about.
Sorry, I'm back.
Okay, so this helps.
Yeah, the connection dropped for some reason.
It happens.
Mhm.
Are you ready to continue, do you think?
Yes, but I heard you were talking about things, so do you want to ask
Lev was just
questions?
asking for kind of a high-level definition of steering, and so Andrew was providing one, but you didn't miss much.
Okay. So I suggest, can you see my screen?
Yes.
So Lev, I remember once I had like a very, very long conversation with Sandu about steering. So maybe if you want to get an idea of it, you could also see what his perspective on the experiment is, because he had loads of questions back then. Mhm. So he might have an interesting perspective that maybe I'm not providing here. Mhm.
Lev, you're muted, so if you want to speak, you have to unmute yourself.
Sorry about disturbance, but maybe still how you would define what is steering, especially you know, when we have a quantum system and we measure one, then it's all clear what happened to another one. People discuss different interpretation, but you want to go beyond it as far as what I understood from the beginning of your lecture. So then tell me what you mean by steering.
So the thing is
changing probability distribution by given outcome. So this is what.
No, so basically what you have is that Bob has, what happens in Bob's lab can be thought of as Bob having like an ensemble of ensembles in his, an ensemble of ensembles of quantum states. Yeah. So what happens, Bob's system can be prepared in a particular state that corresponds to a particular ensemble element of a particular ensemble element. And the thing is that you have all of these, and you want to know if the fact that all of these ensembles could be realized by Alice by performing measurements on her lab. Can we perform these? Can we have access to these ensemble elements by performing a quantum experiment? Or would we need Alice and Bob to share a system which is more powerful than quantum in order to observe these ensembles of ensembles in Bob's lab? Ensembles of quantum systems, there we go.
Okay, I think maybe you'll continue, and then in the end I will try to ask what does it mean ensembles and ensembles. Usually Bob is just one system, it doesn't have I don't understand what's ensemble, but later.
Yeah, we can. All right, so what I was saying before is that now I was going to try and get into a little bit more detail on specific examples, like worked examples. So here, for example, we have Alice and Bob. And we have this kind of Bob with input setup. So here now, because it's a Bob with input setup, then the non-signaling constraints that we have here underpinning our experiment are the following. So when we trace out Alice, so when we sum over Alice's output, then what we obtain cannot depend on her choice of measurement. And also, so that means that there is no signaling from Alice to Bob. But now Bob also has an input. So there is a non-signaling condition from Bob to Alice. And that means that if we now if we trace out, so let's think of Alice. If we trace Bob out of the equation here, so if we forget about him in the whole experiment, then what Alice is left with should be something that does not depend on Bob's choice of input here, or Bob's choice on how to influence the state preparation of his quantum system. So those are the two non-signaling constraints that we have here. And here, actually, we found examples that of things that do not admit a quantum explanation, assemblages that do not admit a quantum explanation. And this is an example of the following. Let's take all of these classical variables to be binary ones, and let's take their values to be 0 and 1. So what we come and define the following collection of subnormalized density matrices here, which is just this. I mean, it's just a particular mathematical expression. And you can check that this satisfies these non-signaling constraints that I wrote above. But now, let's see what happens if now Bob does something else after, getting his quantum system prepared. And is to perform a measurement on the computational basis. And now if we observe the correlations that Alice and Bob would observe in this thought experiment, then this would yield a Pierre box. And we know that the Pierre box does not have a quantum realization. And well, if this sigma of A given xy was a quantum assemblage, then this would provide a quantum realization for a Pierre box, and we kind of don't want that, right? That's not possible. And that is what tells us that this assemblage that we've defined here mathematically is not a quantum assemblage. You cannot produce it with quantum resources. However, so this is quite a nice, clean example of how something post-quantum can emerge in such a bipartite setup. But it's in a way not necessarily an interesting one, because the way, or somehow the fact of the post-quantumness of the assemblage relies or is underpinned by post-quantum correlations in a Bell scenario. So you can argue, well, why have you given me something so complex and complicated that at the end of the day, everything interesting about it is just stems from a Pierre box that we already knew. And that prompts the question of, can we find a post-quantum assemblage that is not implied, whose post-quantumness is not implied by post-quantum correlations in a Bell scenario? So can we find a way to think of, or an example that tells us that post-quantum steering is a different phenomenon than post-quantum Bell non-classicality? And this is the example that I'm going to present you next. And here I should put in big red letters, thanks Pyman 2018, because actually this example came up of chats that we had here and there during the workshop. So thank you, people, for having organized that workshop, because that led to this example. So this is an example of post-quantum steering that does not feature post-quantum Bell non-classicality. And this is the following example. So we have a scenario where Alice can perform 3 measurements on her share of the system, and these measurements are dichotomic. And also the classical variable that influences, that Bob chooses to influence the state preparation of his system is also binary. And now you can go sit down and write down this mathematical expression. And you can check that it satisfies all of the requirements for it to be a well-defined non-signaling assemblage. So now the claim is that this assemblage is a post-quantum assemblage, and also that whatever Bob does in his lab, it will yield, if Bob performs whatever measurement he wants in his system, that would always yield quantum correlation. So if we just transform this into a bed experiment by allowing Bob to perform measurements, then we will not see anything not quantum going on there, even though the assemblage itself is post-quantum. And for this, first notice that this mathematical expression here, or the first step to doing all of this, is to notice that this mathematical expression that we use to define the assemblage can alternatively be written as the following. So this is an alternative assemblage, which is a quantumly realizable assemblage. And this lambda here is a positive and trace preserving map. Not necessarily completely positive. And actually, the one that is given in this example, so the one that we need to use here, is not completely positive. And now, once that you've noticed that, then the calculation goes straightforward. So you have a collection of, you have a measurement for Bob. Actually, you can also think of this as a collection of measurements, but to keep things simple, let's just think of it as a single POVM. And now compute the correlations P of AB given XY that come when Bob performs that POVM in these assemblage elements. And because of this particular mathematical expression for our assemblage elements, then at the end, and the fact that the dagger of a positive and trace preserving map acting on POVM elements gives at the end of the day a another possibly different POVM for each choice of this variable y. This just gives a quantum correlation. So this we have a well-defined collection of POVMs for Bob and a quantumly realizable assemblage. So this gives a quantum correlation at the end of the day. So on the one hand, we have defined an assemblage that whatever measurement Bob does can only always yield quantum correlations. And to check that it's post-quantum, we actually use the steering inequality. I'm not going to get into the details of what these operators, or what the specific operators in the steering inequality need to be. But you can find a steering inequality where if you evaluate it on this example, it gives a value of 0, but that you can prove that assemblages that have a quantum realization will always give you a value for that inequality that is larger than 0.4. So that is a way to certify that this example that we gave up here is does not admit a quantum realization. So next,
we have about
yes.
5 minutes left for the seminar. I just wanted to check on your time.
Yes, so I'm getting into the last bit, so I'm going to try to not be too vocal about it. Sorry for the slight delay in the middle with the internet cut. But yeah, so now that we know that post-quantum steering can be defined mathematically, then we can ask loads of questions. Now is when the whole, you can start doing loads of things with the research. And the first question, which is one of the ones I like asking about all of these phenomena, is whether it's a fantasy or a possibility. So for example, is post-quantum steering a realistic, or could it manifest in some physical theory? And the answer is, well, no to the first one, yes to the second one, because we managed to define a toy theory, which we dubbed Whitworld, which is a compositional theory that that features post-quantum steering as well as quantum one. And this is also something that happened during PyMan 2018. So thank you again for having organized that. And I'm not going to go into the details of this, but basically you just take atomic systems, for those of you who know GBTs, which are classical quantum and box world systems, and combine them via the Max tensor product. And just apply the no restriction hypothesis. And with this very minimalistic view of very minimalistic definition of toy theory, you can already see all of these things. So now that we know that it's not necessarily fantasy and that it could potentially arise in a well-defined physical theory in the future, can we use post-quantum steering as a resource? And something that we also proved by using our toy theory Whitworld is that you can use post-quantum steering to perform remote state preparation better than with quantum resources. And this is, a non-trivial advantage because it relies on the assemblages themselves rather than on the correlation that they can produce. And I'm not going to get into the details of this either, but to, mention it and give it a little bit of an advertising, there is the question, well, if we know that now that it can act as a resource, can we quantify it? Can we, use it systematically? And we have actually developed a resource theory of steering using local operations or shared randomness as the free operations in the theory, which is something that differs from the previous resource theories that had been produced, which actually only apply to bipartite scenarios, and ours applies to all of these families of scenarios. So we started, paving the way to devising a full quantification of quantum and post-quantum steering. And yes, I'm not going to get into the details of the results of that paper, but these are beautiful pictures that you can see if you go and read it. It's by my student, Beata Schiavin. And the last thing that I want to mention is then another question that one could ask, which is, can we take a principled approach to steering and see if we can find, for example, physical principles that single out the set of quantum assemblages and that somehow explain why post-quantum assemblages could not necessarily be witnessed or observed in nature. And this is, something that I was trying to, that I started working with another one of the students in my group, which is Vinicius Rossi. And basically he came and said, this is a very non-trivial question. And so we have a paper out there where we discuss all of the different reasons why it is not, it is a very non-trivial question. So for example, the fact that there exist as post-quantum assemblages with only quantum correlations, as we have seen, means that device-independent principles are definitely insufficient. And things like tomography, which is something that we thought could be good, a good way to, transform these device-independent principles in device-dependent ones, is also not enough. So you need some Hilbert space structure there. So this is a very open question that we still don't know how to tackle, and any ideas or chats about it or discussions would be really, really fruitful. Maybe we need another Pieman workshop for that. So that's it. I talked to you a lot about steering. And maybe I want to give like 3 open questions here to leave you just to, to think about in the back of your mind. So the first one is about activation. So that's one of the open questions of whether there is a way to somehow do something or make some sort of operations to our post-quantum assemblages to somehow distill some post-quantum correlation from them. To see if there is a kind of hidden post-quantumness, in the same way that there was some hidden non-locality sometimes in correlations. And also the second one is, exactly what I was telling you about my project with Vinicius, how to understand, how to use steering to understand better what is non-classical about quantum phenomena. And then the last one, which is what people working on quantum information are very interested about, is there, like, what are the scope of applications that post-quantum steering, for example, could allow us to do that quantum resources don't. So that would tell us, limitations of quantum resources. And yes, that is the group. That is my group here in Gdansk. So here, David, that is in my left hand, that would be, is the second one from the left, sorry. And then continuing, you have Paulo, is a PhD student, is the one that developed the whole Whitworth paper. And then you have Beata, who is focused on resource theories, among other things. She's worked on this paper that I briefly mentioned a couple of slides ago, and this is Vinicius, the next one, who is thinking about this whole quantum from principles. So if you want to know more about the group, there's the webpage. And thank you so much for your attention, and so sorry for going over time a bit.
Okay, thank you so much.
No problem.
All right.
Should I stop screen share, or what do you prefer?
Yeah, maybe
why don't you leave it up and we can have a question or two at the end?
Yes.
I unfortunately have to run off and teach a class. So thank you very much, Belen. I enjoyed the talk.
Okay.
I'll find some other time.
Bye.
Ken, you have a question?
Yeah, thank you. for the great talk. I'm still trying to wrap my brain around the case where you have ordinary Bell inequalities, but you still have post-quantum steering. So let me frame my question this way. Maybe you can help me think about these conditions. Okay, so there is a quantum state that you could construct, an entangled quantum state, that would have exactly the same Bell correlations as your example, right? Okay, so suppose I built that state, and I measure all the Bell correlations and they're all correct. But that must be different from your state, right? Because your state is post-quantum steering. So I guess the question is, what feature am I missing if I just do all my Bell correlation experiments? I'm missing something about this state, right? Because it's different from yours. So what am I missing by only doing Bell correlation measurements?
Yeah, that is a very good question, and that we also were puzzled by it at the beginning. And the key concept here is the dimension. So it might be that in order to find the quantum realizations for the correlations, you need Bob to have a local quantum system that is of a dimension much higher than the one that you request that he has in the steering experiment.
Oh, so you're saying that in order to actually build this state, you would have to go to some higher dimensional space.
Exactly. So in the steering experiment, the dimension of Bob is fixed. So you maybe the dimension that he has is not compatible with the quantum explanation, but if now you have a Bell experiment that tries to explain the correlations that they observe, then you can use the quantum state of a much higher dimension and then explain everything.
I see. But even that state would disagree with your steering.
Yeah, because if you take the state and then if you take the Bell experiment and just just take a snapshot of the situation before Bob performs his measurement, then that would be a steering experiment in a way, but the dimension of Bob's system would be different from the dimension of the steering experiment that we were considering at the beginning.
Okay, I'll think about that a bit more, but
yes,
that's very helpful.
yes.
Thank you.
Thank you.
All right, so I have to run to my next meeting, but I'm going to let you guys continue the discussion. So thanks again, Anna, and we hope to see you here at Chapman sometime soon.
Okay, thank you